So for conservative systems, or for systems that are stable and have a positive stiffness, so K is positive, or the matrix of stiffness is positive definite, then this integral of my original equation, which I call the potential energy of the system, this integral of the equation is minimum at equilibrium. So I'm going to utilize this by, so the Rayleigh-Ritz method does the following. Does the following. Instead of saying g of x equal minimum, x is what I'm looking for, I'm going to assume a certain form for x, again, within the space of a certain functions, within the space of possibilities, polynomials, cubics, whatever. I'm going to put here the possible or allowable forms. Let's say this form is equal to x a naught, x plus a1, x plus a2, for example, a naught plus a naught multiplied by 1 plus a1 multiplied by x1 plus a2 multiplied by x2 divided by x squared, which makes g now a function of a naught, a1, a2. Now, to minimize the function with respect to those three variables is simple. To find a0, a1, and a2, all you have to do is just take partial g by partial a0 and equate it to 0. Partial g by partial a1 and equate it to 0. Partial g by partial a2 equate it to 0. Just minimizing this function with respect to those three variables. So the potential energy of the system, which we are going to minimize, has the following form. It's equal to the potential energy inside the continuum minus the work done by the external forces. The work done by the external forces is equal to the traction vectors on the surface multiplied by the displacement, minus the work done by the body force vectors during the displacement u. So the dot product between u and rho b. And without having to go through details, at equilibrium, the potential energy of the system is minimum because of the choice of having said the structure is stable. Because the structure is stable, and because I'm assuming a certain form for this u, the second derivative is greater than 0, which tells me that the structure is stable. And the potential energy is minimum, which is basically equivalent to what I just did here. That the second derivative is positive. So let's solve a Rayleigh-Ritz method example. We have a bar of length L, constant cross-section area, has a distributed load Cx1. The bar has a constant force of value P applied at this end. It's fixed right here. So we need to find the displacement of the bar by directly solving the differential equation of equilibrium, and we need to find the displacement using the Rayleigh-Ritz method and the virtual work principle, assuming polynomials of the degree 0, 1, 2, 3, and 4. So what will happen if I assume 0, 1, 2, 3, and 4? And we're assuming that it's linear elastic, Young's modulus is A, and we can use the small strain tensor to describe the strain. So we already know how to solve the equation of equilibrium. The equation of equilibrium, I've got here sigma on 1, and I have here this, and this is the force acting per unit length. The sum of forces equals 0. So partial sigma on 1 by partial x1 dx1 multiplied by the area is equal to plus cx1 dx1 equals 0. This is what we did last time. And replace sigma on 1 with E epsilon on 1, which is E du1 by dx1. So you get an equation that says A E du1 dtu1 by dx1 squared equal to negative cx1. I think in the notes I put here divided by 8. This is the equation that I'd like to solve, the differential equation of equilibrium. The boundary conditions are u1 equals 0, and here sigma on 1, which is equal to E epsilon on 1, which is equal to E du1 by dx1 is equal to the force divided by the area. I know the stress at this point, and I know the displacement at this point. So you solve this differential equation with these boundary conditions, and you get a cubic function. So this is exact solution, and what we call strong form solution. The Rayleigh-Ritz method now works on the potential energy of the system. It minimizes the potential energy of the system. And the first thing we have to do for any approximate method is we need to assume something. The only space of displacements that I can find, I'm going to assume, okay, well, let's start with the simplest form. The displacement is constant. And the first criterion is stability of the structure. And the structure is what we call the essential boundary conditions. For this beam, for a beam under axial load, the essential boundary conditions are only the displacement. So at x1 equals 0, u1 equals 0, which will give me this constant equals 0, which will give me the trivial solution. And so this approximation is actually not accepted. because to satisfy the essential boundary condition, you're just going to tell me that the displacement is 0, so the stress is 0, so everything is 0. So we're going to try a better assumption. The displacement is a constant. And notice that any assumption has to include the lower forms. If I restrict my assumption to this, then I'm preventing the structure from having what I call a rigid body motion. So I'm preventing, I can't have a form A1X without including A0. And this restriction will be carried on when I talk about the shape functions for the finite element analysis. They have to allow all the possible strain forms, all the possible lower strain forms. So any displacement function has to allow rigid body displacement, linear displacement, and so on. If it allows linear displacement, it has to allow rigid body displacement, or what we call constant displacements. Okay, first criterion is structures stability. At x1 equals 0, u1 equals 0. And from here, u0 equals 0. This is not always the case, just because it happens that I chose the start of x1 here. If I put it on somewhere else, you will not get a0 equals 0. You'll get a different value for a0. And that's what you have for your assignment. Then u1 is equal to a1 x1. And what is my unknown? I would like to find what constant should I use here so that that would best approximate the displacement. So second criterion, minimize potential energy. What is the potential energy of the system? It's equal to the energy stored inside the beam when it forms minus the work done by the external forces. The external forces are external forces are a distributed Cx1 and concentrated P and reactions, but the work done by the reactions is 0. Why is the work done by the reactions 0?
No displacement.
No displacement, because I already satisfied this. Okay, so U dV, that's equal to sigma 1, epsilon 1 over 2, integrated over the area, integrated over the length. The area is constant, minus. This is a distributed load, Cx1 multiplied by U1, integrated over the length. This is in this way, and this is in this way, and this minus. This is a concentrated load, so minus P multiplied by the displacement at x1 equal to L. So the displacement at that particular point. going to use that u1 is equal to ax1, which tells me that epsilon 1, which is du1 by dx1, is a constant. I'm assuming constant strain beam that has a constant strain. Potential energy of the system will be equal to, now sigma on 1 is equal to E epsilon 1, which is equal to E. So E A1 squared over 2, area, integrated from 0 to L, dx minus C. Instead of U1, I'm going to use A1x1, so C A1 x1 cubed over 3 from 0 to L, minus E multiplied by A1F. EA over 2 A1 squared L minus C A1 L1 cubed, sorry, L1 L cubed over 3 minus PA1 L, and this is the potential energy of the system as a function of the only thing that I don't know here is this A1. Partial. I'm integrating with respect to A1, so you'll get that A1 is equal to PL plus CL cubed over 3 divided by EA. Therefore, U approximate is equal to this A1 multiplied by X. So within the slide, then within the possible linear functions, the best linear function that would approximate my parabolic displacement, or actually my cubic displacement, is when this constant is equal to PL plus CL cubed over 3 divided by EA L. A better approximation. So if you don't like this approximation, try a better approximation. The displacement is equal to A0 plus A1x plus A2x1 squared. First criterion is essential boundary conditions. From here, A0 will be equal to 0. Second criterion is minimize energy. To minimize energy, I need strain. The strain is equal to du1 by dx1, which is equal to a1 plus 2a2x1. This is the strain in the beam, so I'm assuming that the strain along the beam is equal to a linear function, and the stress is equal to E epsilon 1, which is equal to E multiplied by A1 plus 2A2x1. And the potential energy of the system is equal to the integral of sigma on 1 epsilon 1 over 2 area integrated over the length minus Cx1 multiplied by the displacement minus the force multiplied by the displacement, which is A1L plus A2L squared. If you put what you know for the stress and the strain and integrate from 0 to L, you will find this is a function of A2 and A3. Sorry, A1 and A2. For two equations, equation 1 is partial this pi with respect to A1 equals 0. Equation 2 partial pi by partial A2 equals 0. Two equations, two unknowns, and find the best approximation. Again, this will be a better approximation. But if you use if I use this, what do you think A4 and A5 will be? What's the exact? Not very small. They're actually going to be 0. Yes. And so why are they going to be 0?
So the exact equation is the power.
Yes, because within my assumed space of functions, the exact solution actually is within that space. Because the exact solution looks like this. The exact solution looks like this. Zero plus constant multiplied by x1 plus 0 plus a constant multiplied by x1 cubed plus 0. This constant is P over EA plus CL squared over 2EA, and this constant is negative C over 6EA. Because the exact looks like this, when I use this approximate solution, the exact lives in that space. And so when I use this approximate, and I solve for A0, A1, A2, A3, A4, and A5, minimize the potential energy, you will find A5, A4 are 0, A2 is 0, A0 is 0, that's because of the boundary conditions, and you will, when you calculate A1 and A3, you will get these constants. So let's, maybe I'll show you how to do this in Mathematica quickly, and then we're going to go through other examples. Alright, so I'm going to assume U is equal to A naught plus A1 x plus A2 x squared plus A3 x power 3 plus A4 x power 4 plus A5 x power 5. And I should expect that now A naught is 0, that's the boundary conditions. You can just simply say that A naught is 0, but I'm not going to do it that way. I'm going to say solve for A1, that the boundary condition is when U, when x is 0, basically what this gives you is the value of U when x is 0. So when the value of U when x is 0 is equal to A naught, then I want to solve that this equation is equal to 0, solve for A naught is equal to 0, and then I can utilize this, say use U, when you use that first row, and that will just, if your boundary conditions are a little bit more complicated, you might want to do it that way. If you have 10 boundary conditions, for example, then you can replace 10 of your constants using that way. I can put as many equations here and as the number of equations as unknowns here. So now this is my displacement after getting rid of one constant, which is A naught. du by dx is equal to du with respect to x. And the potential energy of the system is what I'm looking for. PE is equal to integrate 1 over 2 multiplied by EA. I'm going to leave EA constant, multiplied by this du by dx power 2. Integrate x from 0 to L. I'm just going to make sure I haven't done anything wrong. I'm just going to run it. So see, it's a huge equation if you want to do this by hand. It's okay to do it for 1 or 2 constants, but by hand for 5 constants, it's huge. This is the potential energy of the system. This is the internal work. This is the potential energy or the elastic energy of the system. The work done by the external forces is integrate. The distributed load is equal to C, constant C, multiplied by X, multiplied by U, when X is 0 to L, minus force P multiplied by displacement when x is L. It's not any displacement, it's a particular displacement. It's the displacement when x is equal to L. Shift enter, you get a huge. Now I would like to minimize this and find a not A1, A2, and A3, and A4, and A5. So I'm going to call equation 1 is equal to the partial potential energy by A1. I will make 5 equations. And I'm going to solve those 5 equations. I'm looking for A1, A2, A3, A4, and A5. Shift enter. I don't need to view these equations. And you get A2 is 0, A4 is 0, and A5 is 0. If I put as many more, that's not, it won't change anything because my exact solution is in fact this equation. Now, if, for example, I'm just going to just throw it in here, this constant is equal to len x, or the logarithmic function of x. Then the exact solution does not live here because the logarithmic of x is I don't know the integral, but the exact solution is not in this space. The exact solution is not in this space, so you're going to get constants for all the values for all the constants. All right. Do you guys have any questions? Would you be able to do this? This is exactly what you have to do for the assignment, but just different boundary conditions, and I switched it around. Do you have any questions? Yes, but
Can you save this file to it?
no, I'm not going to send you this. But it's in these exactly. This exact file is in the notes, so or in the textbook, or it's exactly the same. I mean, I might just change how I write the variables. I use capital X for small x, but it's exactly the same. So in the textbook, I also solved this example again using the principle of virtual work, and using the principle of virtual work is the same thing. You assume U1 a certain form, and you assume U1 star another form. But the only possible form is that, because I only live in this space, so this form is exactly this form, even after I incorporate the essential boundary conditions. Then I equate internal virtual work to the external virtual work. Equating the internal virtual work to the external virtual work, you're going to get a lot of, you're going to get a huge expression equal to a huge expression. I'm going to take everything that's multiplied by A naught star here, and everything that's multiplied by A naught star here. This is equal to this. Now A naught star will not appear because of the essential boundary conditions. So this and this goes. So whatever is multiplied by A1 star here, and whatever is multiplied by A1 star here, equate them to each other. This is equation 1. And this is equation 2. Solve those two equations, and you get A1 and A2. This is just another example. You can take a look at the other examples. And for this particular example, because I've chosen now here no distributed load, the boundary condition is that the stress here is equal to P over A. And the exact solution happens to be a length function, logarithmic function. Because the exact solution happens to be a logarithmic function, the space of solutions that I'm using is just polynomial functions, so they will always, they will approximate, but they will always be, it's never going to be exact. I will never, because my approximations do not include that length function, I'll never get the exact solution. And notice the following. This is, if I assume a linear displacement, this is the first trial. Further trials. Now this is exactly what you do in the finite element analysis. What happens here is that your displacement, your first trial displacement, which is this linear function, when the displacement is linear, what is the strain? What's the order of the strain? The strain is constant, because the strain is the first derivative of the displacement. The strain is constant, and the stress is function of the strain. It's a linear function of the strain, so the stress is constant. And so you get constant stress. Now, I will remind you of this again when we plot the stresses on elements and we find constant stresses on elements. So the stress here is constant. So this is first trial. And what you can see, which is important, is that the first trial produces a displacement that's not so far from the exact, but the stress is really far from the exact. So the derivatives of the solution are further apart than the actual. So I'm looking for u. The difference between u exact and u approximate is usually less than the difference between the approximate and the exact. The difference between the derivative of that solution. And so the further trials here give me very accurate displacements, but this still further trials are far from the stress, and you basically this is the second trial. And now third trial gives you a better approximation. Third trial is along the actual solution for the stress. So u approaches the exact solution faster than its derivative. And when we look at the finite element analysis softwares, all of them, and I will show you this when we go through software, the finite element analysis softwares hide this fact from you. They hide this fact from you when you plot the contours of the stresses. They always give you very nice contours, but they are actually using a lot of smoothing. If you actually go into Abacus, I'm not sure about how ANSYS does it, but if you go into Abacus and you change the slider of the smoothness, you can see how the stresses are very discontinuous. And we'll see it when we actually start using the software. Another example, so you can look at the solution to this example. types of beams that we are looking at: beams under axial load and beams under lateral loading. Beams under lateral loading we're using Euler-Bernoulli beam. And the only difference between this beam and the previous beam is what are the boundary conditions, what are the essential boundary conditions, and what is the form of the potential energy. So essential boundary conditions. So just to follow the same, this is the exact solution. Just to follow the same procedure, this is the exact solution. An approximate solution starts by an assumption. And let's assume that the possible. Of course, I can't use I can't use constants, so I'm going to assume that it's a linear. So basically, I'm saying that the displacement of the beam can only have this shape. Now, within the boundary conditions that I have for the stability of the structure, do you think this is possible or not? It's not possible because this is fixed. Because this is fixed, I can't have this linear displacement. Which can be written as this, to satisfy the essential stability boundary conditions of an Euler-Bernoulli beam. I have that x1 equals 0, the displacement is 0, and at x1 equals 0, the rotation, which is the first derivative of the displacement, is also 0, which tells me that y is equal to 0, the trivial solution. So, not acceptable. Second attempt. Y is equal to A0 plus A1 x1 plus A2 x1 squared. First criterion is essential boundary conditions. A0 will be 0 and A1 will be 2. Which means I'm assuming that this is my displacement of the beam. So the first difference between this and the previous problem is the boundary conditions. The boundary conditions in the beams under axial load was just the displacement. Beams under lateral load is the displacement and the rotation. Second criterion is minimize potential energy. Potential energy of the system is written as follows. The strain energy inside the elastic object, which is similar to kx squared over 2, minus the work done by the external forces, which is similar to mgx. The work done by the external forces, I'm going to look at the beam. The external forces are the reactions and the external force P. The essential boundary conditions will make the work done by those reactions 0. I'm only left with P. So minus P, this is negative because it's acting downwards, and the displacement is A2 multiplied by L squared. This is the displacement when x1 is equal to L. So this is equal to the energy term here is different from the energy term before. The energy term here is EI d2y by dx1 squared over 2 squared. Integrate over the length. Plus P A2L squared. The second derivative of the displacement is equal to 2A2, so this is equal to EI over 2A2 squared dx1 plus P A2L squared so minimize potential energy, partial potential energy with respect to this unknown A2 is 0. From here you get A2 is equal to negative PL over 4 EI which tells me that the displacement is equal to negative PL over 4 EI x1 squared. Yes?
How to get the equation for the energy of the beam under moment?
I'm going to just scroll up all the way to here and utilize this one. It's the linear elastic strain energy in Euler-Bernoulli beams with small deformations. I started with sigma 11 epsilon 1 by integrated and replaced the stress and the strain with functions of the moments and the second derivative with the displacement and reached this equation in terms of the moment rather than in terms of the stresses. You could do it in terms of the stresses, but we only deal with moments and y. In the beams, we replace the stresses and the strains with moments and d2y by dx1 squared. They're the same thing, but just integrated. Because the moment and the stress are related with that, and the strain. And this, I don't remember the exact equation. They're just functions of each other. Okay? So this is the displacement, and from here you get that the moment is equal to constant, which is equal to EI, the second derivative of y with respect to x1. This will be equal to negative PL over 2, and the shear, which is dm by dx, is equal to 0. So your approximation, or the approximation, is predicting 0 shear on the beam. When the beam is actually has the only, it has a constant shear, but because I restricted my approximation to only this parabolic function, I was not able to predict shear. And you have another example in your textbook with a simple beam, and again, you're approximating the exact. So this is how you're approximating the displacement with an exact, with a second order, third order, fourth order. You're approaching the displacement from below, and this is your first trial, and as you get better, you're getting better approximation. First assumption for the first trial for the moments, you get a constant moment and zero shear. And then as you put in better approximations, you get better or closer to the exact solutions. Okay, so we'll give you 5 minutes.